Hi there, folks. Today we're looking at correlation, causation, and assessing fit. And essentially what we're going to do is we're going to investigate these lines of best fit that we've been talking about. We're going to look at them from the perspective of, okay, now that we've talked about correlation, is there a relationship that goes beyond correlation, all right? Is there a cause and effect type of relationship? And then we're also going to go into looking at those lines of best fit and determining how accurate they are. Okay, so this first idea of causation, so we've already talked about correlation. Correlation is just when we see a pattern strictly based on the numbers, all right? As one value goes up, the other one goes up. That is positive correlation, okay? As one value goes up, the other one goes down. That's negative correlation. But now we want to look beyond that. We want to look at the units that we're talking about, the variables that are represented, and we want to know if there's a cause and effect relationship that's causing that correlation, all right? So causation is if correlation is a result of the relationship between two of the variables, all right? In other words, is one of the thing causing the other thing to go up or down, all right? And that's the thing we want to investigate. We can have correlation, but not have any causation, all right? And so that's what we want to look at. We want to make sure there's causation because the fact of the matter is, if we have correlation, we can write the equation for a line of best fit. Okay, but that line of best fit is kind of useless in terms of making predictions if there's no causation. Okay, so anytime there's correlation, we can create a line of best fit, but that line of best fit is only useful if there's some kind of causation, and that allows me to use that prediction equation or that line of best fit to make predictions. Okay, for example, if I look at something like this guy, I want to just determine if there's correlation, first of all, and then secondly, is there causation to back that correlation up, all right? And so if I look at something like this, we've got the years 2004 through 2008. I have album downloads, so we're downloading music. And then I have e-tax returns, which are just tax returns that you file online through something like TurboTax or whatever, all right, instead of doing like a paper copy. All right. And so when we look at this, the album downloads, as we look from 2004 to 2008, are increasing. All right. So we have a lot more album downloads happening as the years go on. And then we look at e-tax returns, online tax returns, and we notice those are also going up. Those are increasing as time goes on. So if we compared the album downloads and the e-tax returns, they're both increasing together. So there's positive correlation there. As one goes up, the other one is also going up, right? And if we looked at that on a scatter plot, if they're both increasing, we would have positive correlation. And so I'm going to put positive correlation for this one. But now I want to look beyond correlation and determine, okay, I understand that there's positive correlation, but is that positive correlation, is one of those things going up caused by the other thing going up? All right, is there causation? And so as I look at this, as the album downloads went up, the e-tax returns also went up. So now I want to ask myself, do the album downloads going up make the e-tax returns to go up? Do they cause that to actually happen? And when you think about it, so downloading music versus how you file your taxes, do those have anything to do with one another? And the answer is no. Downloading music and tax returns don't really have anything to do with one another. There's no causation here, all right? Yes, there's positive correlation, all right? As one goes up, the other one goes up, but there's no relationship between cause and effect, all right? The number of album downloads doesn't make e-tax returns go up, okay? It's kind of a coincidence that they're both increasing together, all right? So they have correlation, but no causation, all right? So I'm going to put no causation here. And this is one of those things that's kind of used and abused really in statistics, is people will present numbers and say, oh, there's a positive correlation here, and make the assumption that means there's a cause and effect kind of thing. For example, I could say that the price of a gallon of milk has increased over time, but something like black rhinos, the population has decreased over time. Now they're an endangered species, all right? And so the idea here is, well, if I were to abuse those statistics, I would say, see, the cost of a gallon of milk is causing the extinction of the rhinos. And that's absolutely not true. Those have nothing to do with one another. There's positive correlation, but there's no causation. There's no cause and effect there. Okay, and there's a big difference between these things, and it's one of those things that people will assume that if there's positive correlation, and they'll present statistics that have positive correlation, all right, and they'll assume causation, all right, but we can't make that assumption. We have to look for underlying factors that show that there's causation. Okay, how about something like this guy? If we look at something like this, we're talking about basketball players, 6 basketball players in a particular game, and we're looking at their minutes played and their points scored. Okay, and as we look at these aren't written in order, but if I start to kind of look at them in order, right here the lowest number of minutes played was 18, and there was 5 points, and then 25 is 7 points, and then we have these 30s at 11 and 14 points. And then the 31 is 13, and the 33 is 13. And so as we look at this, and as you kind of visualize maybe a scatter plot here, all right, as we go to those lower number of minutes, the points generally tend to be lower. And as we get to the higher number of minutes, the points generally tend to be higher, all right? And so as the minutes go up, the points, for the most part, go up. So we would say there's a positive correlation here. But now we want to go further than that and say, okay, there's positive correlation. In general, as the minutes go up, the points go up. But is there causation? All right. Does the number of minutes played tend to make the number of points go up? All right. And so when you think about this, this one, there's definitely a relationship between being in the game and being able to score points. And for somebody who scores points in a basketball game, the more minutes they play, the more opportunities they will have to score points. And so this one, we're going to say there is causation here. If you looked at a basketball player like Michael Jordan or LeBron James or something like that, and you looked at the number of minutes played versus the points scored, generally, if they only played 5 minutes of the game, the number of points scored is going to be low. But if they played more and more minutes, they should be able to score more and more points because they're a scoring type of basketball player. And so we're going to say there's a positive correlation. Yeah, it's going up, but there's also causation here, okay? And there's causation because there's a direct impact from the number of minutes played on the number of points that are typically scored. Okay? It doesn't necessarily mean that if you play the whole game, you're going to score more points than you ever have. Okay, you could be having an off night, but in general, all right, if you are kind of have an average for scoring, the more minutes you play, the higher your points are going to be because you're going to continue to accumulate. Okay, there is a relationship there, and that's what we're looking for. If we look at something like this guy. I've got drinks, hot and cold drinks sold from June to November, all right? So the number of hot drinks sold from June to November, we can see is steadily increasing from 100 to 150 to 200, 230, 250, okay? So it's gradually increasing. The number of cold drinks from June to November is gradually decreasing, 300 to 210 to 175. And so as the hot drinks are going up, the cold drinks are going down. Well, that represents negative correlation. As one thing goes up, the other one goes down. And if we visualize that on a scatter plot, we would see negative correlation here. So I'm going to say negative correlation. But now we want to go beyond that and say, okay, is there causation? All right, so there's a negative correlation as the number of hot drinks increase, the number of hot drinks sold increase, the number of cold drinks sold decreases. That's negative correlation. But does the number of hot drinks sold cause the number of cold drinks sold to go down? Does selling more hot drinks necessarily make the number of cold drinks sold go down? All right, and this one's not quite as cut and dry as we look at this thing. And, you might say, well, if they can only sell a certain amount, let's say their potential for selling drinks is really unlimited, all right? Is selling more hot drinks making the cold drinks to go down? When you think about what's causing the number of hot drinks to increase and what's causing the number of cold drinks to increase, it's not the number of the other drinks. It's the exterior temperature probably that we're looking at. The fact that this data is June through November, when the temperature is going from hot and then starting to get colder, all right, as we get into the fall and into the winter, all right, Well, that's going to cause the number of hot drinks to increase, not necessarily the cold drinks, and selling less of those. And the cold drinks, yeah, people are going to tend to shy away from those as the weather gets colder. So it's not necessarily the relationship. There's not necessarily a causation relationship between hot and cold drinks. All right, the causation is between maybe the exterior temperature and the type of drinks that people are buying. If we were to graph each of these separately, if we looked at the exterior temperature versus the number of hot drinks, we could maybe say that there's causation. Or if we looked at the outside temperature versus the number of cold drinks sold, then we could list this as some kind of causation. Okay? So even though there's a negative correlation, it's not necessarily causation here. So I'm going to say no causation. All right. But it would be really easy to kind of misuse these statistics and say, hey, the number of cold drinks sold really is affected by the number of hot drinks. Well, no, it's other factors that are really affecting the number of sales here. Okay. Just so happens that there's a negative correlation between those two things. All right, next here we're going to look at kind of assessing fit, all right? And we've done this a little bit. We've made judgment calls kind of about which lines of best fit are better and how we would adjust lines of best fit to make them better, all right? But now we're going to look at these from the perspective of residuals, all right? And we're going to do these things called residual plots. And all a residual is basically measuring, all right? It's a measurement. See, we've been kind of just using judgment calls and saying, I need to adjust the line of best fit in this way. Okay, but now we're going to use actual measurements to show those adjustments, okay? And a residual is just a measurement of the difference between the actual value and the predicted value. It's basically showing us how far off our predicted value is from the actual data values that I have, okay? And see, we'll typically use, equations, our lines of best fit, and those prediction equations to make predictions about future values. But right now, we're going to use those equations to look at the comparison between what our equation would give us and what the actual data presented us with, okay? And that's kind of what residuals do. They show us the difference between what we have and what we expect to have based on our equation, okay? For example, if I look at something like this guy, here I have shoe size and height, all right? And there is a positive correlation between shoe size and height. Typically, as shoe size goes up, the height of the individual also goes up. Okay, and so there's a positive correlation here, and there's also causation here, all right, because really these things have a relationship. The bigger a person is, the taller they are, usually the bigger some of their features like their feet are, okay, or their wingspan from fingertip to fingertip is usually equal to your height. And so as your height increases, well, your arm length also increases. And so there's this natural relationship there. There's causation, okay? And so if I look at something like this guy here, I have this thing plotted already. So there's my scatter plot. I have 3 lines of best fit drawn, okay? And we could probably look at this very quickly and say, okay, I think the line in purple is the best line of best fit that I have drawn here, okay? And most of you would probably agree with me. As we looked at the line in light blue there, it looks like that line has a pretty decent slope, but it's up too high, so maybe the y-intercept is a little off. The line in orange there looks like it's got an okay slope, but maybe that slope is just a little bit low, so maybe that slope needs to be a little bit higher. And so that idea of how do we adjust these lines of best fit to make them better, we can kind of make a judgment call and estimate that just by looking at the graph. But a residual is going to give us more data in terms of what we're talking about right here. Okay, so residuals are going to show us how far off and give us numeric values to make adjustments for this thing. For example, so here's what we do for a residual. I basically plug each of these into my equation. So like if I were to plug this 7 into the first equation, I get a 63.8, okay? If I were to plug the 8 into that purple equation, I get a 65.6. If I were to plug, again, the 8 in, 65.6. If I plug the 10 in, I get a 69.2. If I plug the 11 into my equation, I get a 71. If I plug the 12 into my equation, I get a 72.8, okay? See, that's what I would get for each of these shoe sizes using my prediction equation, using that equation in purple, okay? And so the idea here is I want to compare my prediction which is like for this first one, the 63.8, I want to compare that prediction to the actual data value, which was 62. And so what we do in a residual is I essentially just subtract these things to see how far off I am, to see how close I am. And so when I subtract this one, I get a negative 1.8. When I subtract this guy, I get a negative 0.6. When I subtract this one, 2.4, negative 1.2, 2.8, a 1, and a negative 1.8. And there's a couple of things that we can point out here. One, again, it's showing us how far off we are from the predicted value. And if you look on your graph, so right here, when you compare this line to this point, we can see that the point is negative 1.8 units below the line, okay? And that's why we get a negative 1.8 for the residual. Right here, when we look at this guy, we get a residual of negative 0.6. Well, that's because the point is 0.6 below the line. That's how far off it is. It's off by 0.6 in the negative direction. If I look at the next one, the one that's floating up in space here, that one's higher than the line, so I get a positive 2.4 for the residual. It's just telling me that the actual value is 2.4 units higher than what my line is telling me the value should be, okay? And so that's what these are telling me. This one right here, that's the negative 1.2. Right here we can see that's the positive 2.8. It's showing me how far off I am from the prediction line. So the prediction line is saying one thing, my actual data value is saying another thing. And basically the residual is just measuring how far off they are. It's how different they are. Okay? So here's what we're going to do with this information. We're going to plot these on a residual plot. Okay? Instead of comparing them on the actual graph here, because there's a lot going on, what I do is I do this kind of, it looks almost like a T-chart. Okay? And I'll plot the values we talked about in a second. But when you look at this thing, basically in a residual plot, this guy right here, that represents my line of best fit. Okay? So if we kind of think of it this way, I'm taking the line of best fit and flattening it out, and then replotting those points. And so when we look at a residual plot, the first residual that I had was a negative 1.8 right here at 7. Okay? And then at 8, I had a residual of negative 0.6, which is just below this line. But I also had a residual of 2.4, which is up here. At 10, I had a residual that was at negative 1.2, so right about here. And I also had one at 2.8, just right about here. At 11, I had a residual of 1. And at 12, I had a residual of negative 1.8. Okay? And this is what we call a residual plot. I'm basically just showing how far off those points are. And yeah, it's displaying the same thing that I had up here. It's still displaying this difference and this distance between the line and the point, but it's doing it in a way that allows me to analyze it a little bit more closely, okay? So it's just showing me the difference and the distance between my line of best fit and the actual points that I got, okay? And so when we look at this one, we kind of look at the spread of this thing. Well, looks like those points are pretty close to the line of best fit as we kind of generalize this thing. And I don't see any issues in terms of a pattern with these points in terms of the residual, in that, it looks like my line of best fit is getting worse as we go or getting better as we go, that kind of thing. And so that's kind of what the residual shows me. It gives me a very mathematical depiction of how good this line of best fit is, all right? And, when you look at this one, maybe it's hard to tell. Let's look at one that's not as good, all right? If I look at the line in blue this time, all right, so let's do the line in blue. Let me erase these guys. I'm going to do the same thing for the line in blue, and I'm going to plot it down below. All right, so if I did the line in blue this time, the line in blue, let's see, when I plug a 7 in, I get a 67. Here I get a 69. When I plug the 10 in, I get a 73. 75, and a 77. And so once again, I'm going to subtract these. I'm going to see how far off my blue line is. And right away, before I even subtract these, hopefully you understand that all of these should come out negative, because when I look at the blue line, all right, all of the data values are below the line, okay? They're all shorter. They're all smaller than the line, so that means I'm going to be in the negative direction. And so as I subtract these things, let's see, I get a -5, -4, -1, -5, -1, -3, and a -6. Okay? Those are the residuals for this thing. And again, it's just measuring how far off this is. Like right here, here's that -5. Here's that -1. Here's that -4. It's showing me how far off my data values are compared to the line that I'm trying to use as a prediction. Okay? And so if I plot these guys on the residual plot, so once again, let's see, -5, that's down here. And then 8, I had a -4. And I also had a -1. 10, I had a -5. And I also had a -1. 11, I had a -3. And 12, I had a -6. And so once again, when you look at this thing, it kind of looks like the first residual plot. The big difference here is that all of my values are below my line. And again, this guy right here, this horizontal, now represents my line of best fit. And I'm comparing to that line of best fit to see how far off or how close I am. And so when you compare these residuals, when you look at the pattern of the points, it kind of looks the same as the first one, meaning that this is a pretty good line of best fit other than the fact that the line is too high. It's above all of my data values, and that's what the residual shows me. Okay? If that line was right down here instead, well, that would be a lot better. And so even mathematically, it's showing me how far I would need to adjust this thing in order to get a better value here. And so when you look at this, I'd probably want to lower this by maybe a -3 or so, all right? If I were to kind of look at this, or maybe like a -3.5. If I were to come down here, if the line was here instead, if I lowered that line -3.5 units down, it would be a really good line of best fit. It would now look just as good as my first equation, okay? So not only does it show me that I'm off, but it can show me how far off I am. It gives me a more mathematical representation of how far off I am so I can make adjustments, okay? And so now let's do the last one here. If I do the last guy, once again, let me erase these and I'm going to start over. The last one is probably not that bad of a line of best fit. It's a little bit off, and we're probably, when we compare it to the line in purple, we can see the difference there is that the line in purple has a slightly larger slope. So right away, we already know the issue is the slope is a little off, okay? And so let's see what that looks like on a residual. So if I were to plug each of these values into the last one here, I get a 63.75, or sorry, 0.25, a 64.75. And again, this is just me. I'm plugging the 10 into that equation. Now I'm plugging that 10 in again. That's why I get the same value a couple times. I plug the 11 in. And I plug the 12 in. Sorry, 0.25. Sorry, 7.5 on that one. And now I subtract these. Ready? So when I subtract, this is the residual. This is showing me how far off I am. And so when I subtract these, I get a -1.25, 0.25, a 3.25, 0.25. Okay? And so as I look at that, once again, it's showing me this, like right here, the difference between the red line and this dot. Well, the dot is down 1.25 units. Right here, the green dot is up 0.25 units. All right? Right here, this green dot is up 3.25 units. It's just showing me how far off my data values are compared to the line. Okay? And so now, once again, I'm going to graph these down here. So again, this represents my line of best fit, and then the residual is showing me how far away from the line of best fit I am. So let's see. I had a -1.25, right about there, and then I had a 0.25. At 10, I had a 3.25. Or sorry, that was at 8. Sorry about that. 3.25. Then at 10, I had a 0.25 and a 4.25. At 11, I had a 2.75. And at 12, I had a 1.25. And so this one is interesting because it's not quite as kind of spread out as the other ones were. When you look at the other ones, they're pretty evenly spread. But this one kind of has an upward trend. As you look at this, you might look at this and say there's positive correlation. You might look at this and maybe try drawing another line of best fit and say, hey, the values are increasing as I go. All right? And so the idea here is if the values are increasing as we go, if the values essentially then are getting further and further off. If we looked, the first couple values were close, but then we got a little bit further off, and if we kept going, we'd probably see values that were even further off, that were way up here somewhere, okay? And what that's telling me, because there's a trend, all right, and yeah, it's still a linear trend on this thing, but it's showing me that I'm getting further and further from where I need to be. Well, that happens when the slope is off, okay? See, because when the slope is off, I might start really close to the values, but as I get further and further out, if the slope is too low, my predictions are going to get smaller and smaller than the actual values, okay? I'm going to keep falling further and further short of what the actual values are. If my slope is too high, then my predictions are going to keep getting bigger and bigger and bigger compared to reality, all right? And so that's what the residual plot shows me. As soon as I see this slight upward trend in the points, it's showing me that the slope is off, okay? And since it's a slight upward trend, it means my values are getting too big, which means my slope is too small. Okay? The actual data is outpacing, is getting bigger than the predicted values, which means my slope is too small. I need to increase my slope in order to catch up with those actual values. Okay? This is residual plots. All right? It's still doing the same things that we've been doing, making a judgment call about our line of best fit and determining how close our line of best fit is, but it does it from a more mathematical perspective. It allows us to see actual numbers in terms of these comparisons. Okay?